In this short video, we'll just provide a little bit of justification for why the y equals k1 e to the lambda 1 t v1 plus k2 e to the lambda 2 t v2 solves the system dy dt equals ay. So here's where it makes sense to work with the vector form. So if there are two things that I need. I need to make sure that when I plug in what y equals for y here, and when I plug in the derivative of y over here, that the two sides are going to be equal to each other. But what I don't yet have is the derivative of that vector y. So dy dt, that's going to be the derivative of the right-hand side with respect to t. So k1 e to the lambda 1 t v1 plus k2 e to the lambda 2t times v2. Now the thing that we need to note is that v1 contains numbers in it. This is a constant vector, and so is this. This is a constant vector. With that being said, because the k1 e to the lambda 1 t multiplies both the top and bottom component of v1 and multiplies the top and bottom component of v2, the only function, these are just going to be constants that are going to come out in front of k1 as that multiplies into each of these two vectors. So to take the derivative of this, since that's a constant vector, all I need to worry about is taking the derivative of the functions of t. Again, k1 times this component right here will produce some number times k1 e to the lambda 1t, and this number times k1 e to the lambda 1t will produce another coefficient. So to take the derivative of this is just going to be lambda 1 will come down because it's the derivative of e to the lambda 1t. Using the chain rule is going to be lambda 1 k1 e to the lambda 1t. And since v1 just contains constants, those constants are going to stay there. We're not adding constants, we're scaling by constants. Same thing for the second term, that's going to be lambda 2 k2 e to the lambda 2t times v2. And so now what I need to do is, we said that we need to substitute in dy dt into the left side and to show that these two things are equal to each other. So I'll do just that. So that means dy dt, if it equals a times y, and this is in fact the solution, then I should be able to plug in dy dt, which is the lambda 1 k1 e to the lambda 1 t v1 plus lambda 2 k2 e to the lambda 2 t v2. And now I'm going to say equals with a question mark over the top of that, because I haven't proven that these two things are equal yet. I'm just testing to see if they are. Equals a times y. Okay, well, what does y contain in it? It contains the piece that's shaded in green, so I'm going to replace that with its expansion. So that's going to be a times k1 e to the lambda 1 t v1 plus k2 e to the lambda 2 t times v2. So it's hard to see that these two sides are equal to each other because I have an A matrix here, but I don't have an A matrix on this other side. So what's the significance of these being eigenvalues and eigenvectors? So the one thing that eigenvectors have, or the properties that they have, is that whenever you take an eigenvector, times v, that equals lambda times v. So that means that if I take a times v1, that's equal to lambda 1 v1, and a times v2 will equal lambda 2 times v2. So that's going to be key in showing that these two sides are identical. So there are a couple of ways I can do this. I'll work on the right-hand side. I'm going to distribute that a, and that a matrix can pass over any constants. That's one feature that we can use here. And A is going to multiply past the constants over here. And so what I'll end up with on the right-hand side is, let me just go ahead and expand that right-hand side and show that it ends up being equal to the left-hand side. If I distribute that, I'll have k1 e to the lambda 1 t times a times v1 plus k2 e to the lambda 2t times a times v2. And because a v1 is equal to lambda 1 v1, this is lambda 1 v1, and this equals lambda 2 v2, the special properties that these eigenvectors have. And now I can see that if lambda 1 is just a constant, so I can pull that constant out past the k1, and I get lambda 1 k1 e to the lambda 1 t v1 plus lambda 2 k2 e to the lambda 2t times v2. And I see that this side and this side are now totally equal. And so that proves that this solution works. And this wouldn't work unless these were eigenvectors, because we were relying on this recall statement that if v is an eigenvector and lambda is an eigenvalue, that we satisfy the eigenequation a times v equals lambda v. And we needed to make that replacement here so that we could get everything in terms of lambdas and v's.